All right, so last time we left off talking about resource-bounded computation. We said that not only we're interested in what can or cannot be done algorithmically, even in theory, but how fast, how efficient we can do these things in terms of time, space, and perhaps other resources. So we said the language is decidable in a certain time asymptotically if it can all be recognized by always halting Turing machine within that time asymptotically, that time as a function of the input size. So the input is size n, and the function is t of n, t for time, s for space, and they're independent measures. And we said there's 4 classes of complexity measures, one for deterministic time, one for non-deterministic time, deterministic space and non-deterministic space, and they're called d time t of n time t of n, and so on. The difference with these two is non-determinism is allowed, and sometimes 2 classes, deterministic and non-deterministic, could be the same, but sometimes we don't know. Sometimes it's an open question. P is equal to NP is one of those questions. Whether determinism, non-determinism, there's a difference between them with respect to polynomial time. That's literally $1 million question. And these are all properties. There are sets of languages, which means they're undecidable properties by Rice's theorem, because they're not trivial, any of them. And we said that the time depends on the number of tapes, but the space doesn't, because you have several tapes. You can interlace them, and basically you need a tape just a constant factor larger than the original tapes. That constant is equal to their number. So we said that space doesn't depend on the number of tapes, because you can interlace them. That's another way of saying it, right? Dovetail through the tapes. Just use one tape, and worse off asymptotically. So from a fixed number of tapes, you can go to one tape without loss of asymptotic speed. For time, it's not so clear. If you have more tapes, you can actually save some time. And we gave an example of a language which we can recognize more efficiently if we had more tapes, or more efficiently even if we stuck with the same number of tapes by eliminating every other one, every other 0, and only take a log number of steps. So with some clever algorithmics, you can reduce the time, reduce the space, and that's basically algorithm design and or programming. So without harping too much on these details, every language that's regular, it's also in deterministic time linear, because there's a finite automata that in linear time does its job, recognizes or rejects every single string, right? One state change per character, that's a linear time algorithm. And it's in space constant, right? Because finite automata doesn't have any space. It doesn't have a tape or a stack or any other space. It just states. Finite number, fixed number, finite number of states to recognize a particular language. So a few other examples. Palindromes can be recognized in quadratic time on a single tape machine. Just go back and forth, match characters to characters, and before you know it, you know if you have a palindrome or not. But you don't need more than linear space to do that. So there's some more examples. You could use logarithmic space. I'll let you think about why that's the case to recognize palindromes. So a few special time and space classes that we know and love. P is defined as the union of all deterministic polynomial time classes. So the union of linear time and quadratic time and cubic time and quartic time and quintic time and so on, all possible polynomials stuck in there, the union over all of them, that's what the definition of P is. Intuitively, it's any problem or language that can be recognized in polynomial time. Time polynomial in the size of the input, right? Some fixed power like square or cube or what have you, but not exponential and not factorial, just polynomial. Okay, so that's P, and that's deterministic. Okay, so we're measuring deterministic time to be polynomial, and that's the definition of P. The definition of NP is very similar, except we throw in non-determinism as an option, and that gives you all non-deterministic classes, all polynomial bounded non-deterministic computations. That's all of NP. And each one is an infinite set, right? It contains an infinite number of languages. For example, it contains all the regular languages, because that's just constant time. That's certainly less than polynomial time. Well, constant is a polynomial. It's a very, very low order polynomial. It's a 0th degree polynomial. That's what a constant is. Right? And the nice thing about these classes is that they're robust. They're independent of the model of the computation. Right? So what that means is the same class of polynomially recognizable languages or polynomially solvable problems is the same for a supercomputer as it is for an abacus, even though one is a billion times faster than the other. That billion is a constant, and it gets lost in the asymptotic notation. It's a big constant, don't get me wrong. A billion is a large constant. But so P and NP are independent of whatever model of computation we want to use, whether it's an iPhone, a supercomputer, counting on your fingers, or whatever. These are all independent of each other. P and NP is the same exact class of languages for all these models of computation, including DNA computers, Boolean circuits, game of billiards, all these other models that we talked about when we mentioned universally computable universal Turing machines or computational universality. We said there's a lot of models of different computation techniques. We don't have to use silicon. We can use proteins. We can use water pipes. We can use Tinker Toys, Legos. P and NP is the same class for all of those because they're all polynomially transformable to one another. How many sort of get that? Oh, good. That's a lot of you. Thank you. That's great. All right. Now, we know that P is a subset of NP. Why? Because determinism is a special case of non-determinism. Right? Non-determinism is you can have several choices at your option, but making one choice is a special case of allowing you to make several choices. So P is a subset of NP, but whether they're equal or not, we don't know. It's literally $1 million question, $1 million bounty from the cash from the Clay Institute of Mathematics. It's been an open question since the early 70s. Other special named classes that we talk about a lot is polynomial space, and that's the union of over all polynomial space complexity classes, linear, quadratic, cubic, and so on, union together. You can take infinite unions, it's okay. And NP space is the same, but non-determinism thrown in there in red. So it's almost identical, except you allow non-determinism. And of course, you get an immediate theorem that P space is a subset of NP space because, again, determinism is a special case of non-determinism. You don't lose anything. The question is, do you gain anything? And it turns out it's equal. It's not obvious, actually, that P space is equal to NP space. It's called Savage's theorem. If this was a graduate course, we'd actually prove that. As it stands, I'm not going to attempt that. It's a deep theorem. And you know me well enough by now to realize when I say it's a deep theorem, I mean it. But that's what it is. For space, we know the question of non-determinism equal to determinism. This is the PNP question, the analog of the PNP question, but for space instead of time. And that's, we proved it in Savage's theorem, it's called. For extra credit, you can look it up and tell me what you think. And of course, exponential time is the union over all exponential deterministic time classes, and you can take a non-deterministic version of it too, and you can take exponential space and logarithmic space, and on and on and on, define all these classes. Now we're rolling with these definitions. You can make a lot of classes, new classes, and name some of them, like we did here. And there's, of course, an infinite number that don't have names, because there's only a finite number of names that we can think up, because we only have a finite number of time to do that. But there's a lot of them that have names, hundreds that have proper names, because we discuss them so much and do research about them and solve and pose open problems about them. So, basically, a few time-space relationships. It turns out that, if you have more space than time, you can do more. So any time complexity class is embedded in the same functional space complexity class, because having more space is at least as good as having that time, right? So if you have, f of n units of space, you can certainly expend f of n units of time in that space, and perhaps more, because space is reusable, time isn't. Right? So you have this proper containment, not necessarily proper, but containments nevertheless. It may or may not, some of them may or may not be proper. Quality may or may not hold. We don't know for some of them. For some of them we do. And of course, non-deterministic time is contained in deterministic space. And to get from non-deterministic time to deterministic time, suffice it to exponentiate. Why? Because you can always take a non-deterministic computation that bifurcates into this big computation tree with lots of choices at every node. That's non-determinism. You can make it deterministic by following all the threads. And all you're doing is folding out, spelling out, expanding out that non-deterministic tree layer by layer by layer, taking maybe an exponential number of paths, but eventually you'll compute the totality of the non-deterministic function. In other words, you follow all possible branches of the non-deterministic tree. You do it deterministically. And yes, you'll pay through the nose, but only an exponential factor. And I say only because an exponential factor is a lot, but it won't be more than that. And for some classes, for some conversions and transformation, it is more than that. And here, it's not. So exponential is a lot, but at least you know it won't be more than an exponential to convert non-deterministic computations to a deterministic computation. It's like a power set construction, only for arbitrary computations, not just finite automata. How many get that? Okay, it's a bunch, good. And lots of theorems. Savage's theorem I mentioned, but here it is, the statement of the theorem at least. I'm not going to prove this. It's complicated. But basically, to get rid of non-determinism in space, you don't need to exponentiate the time like you do for time. You don't need to exponentiate the space like you exponentiated the time to get rid of the non-determinism, this pesky little n here, the non-deterministic red n. Suffice it to only square the space. That's what Savage's theorem says. And from that, we have a corollary that non-deterministic space is the same as deterministic space, polynomially speaking. So that's the P is equal to NP question for space, and that's solved. There's no $1 million for that. Just a nice paper back in the 70s. Okay, so here's the map so far. Remember, we had this containment structure. This is a Venn diagram. It sets. Some of the containments are proper, some we don't know, but they're containments nevertheless, as a Venn diagram ought to show. And we know that you have the regular languages, which are a subset of the context-free languages, which are a subset of P, which is a subset of NP, because non-determinism is a generalization of determinism. That's a containment right there. And then all of that can be solved in polynomial space. And of course, all polynomial space can be solved in exponential time because you can follow all the paths from the computation tree deterministically, even though the tree is not deterministic, by following all the paths. And that's an exponential process. Yes, so you'll exponentiate the space to get the time, but you can do it deterministically now. And of course, there's exponential space beyond that, and space is worth more than time because space can be reused, time cannot. A good rule to live by, good philosophy. And of course, all of those are decidable because at least you can do it brute force, whether it's exponential or polynomial time, doesn't matter with respect to decidability, because the point is you can do this. Brute force if necessary, but it's not undecidable. And outside of that, there's still undecidable things like the halting problem in H. And the complement of the halting problem is not even recognizable, and that's H bar here. And all these are examples, the green ones, are examples of a problem that's in that class, but not in any class below that, necessarily. So these are like distinguishing problems, like A to the n, B to the n is deterministic context-free, but not regular. And A to the n, B to the n, C to the n is not even context-free. So it's still polynomially time-solvable, but not by a push-down automaton. Okay, so that's the map so far. But now, let's augment that map. We'll show that map again, but this time we'll show a lot of other complexity classes that have to do with these classes we just defined: linear time, quadratic time, d of n, deterministic time sub function f, deterministic space, and so on. So I want you to understand that in this map, it's not as simple as it looks, even though there's a lot going on so far. There's even more going on here, because there's a whole hierarchy of languages in between these classes. And this time, I'm showing you the purple ones, not as a lot of ovals wrapping each other. So now I'm sort of defecting from the Venn diagram nature of the slide slightly, otherwise it'll get completely messy. But there's infinite hierarchies. Each one of those red hierarchies is an infinite hierarchy around the complexity class that it's adjoining. So there's an infinite number of classes: quadratic time, cubic time, quartic time, time to the n to the fifth, to the sixth, and these are all properly contained. We can prove, we won't prove it in this class, but if this was a graduate course, we would prove it. It's based on diagonalization, basically, that there's an infinite hierarchy of time and space complexity classes within P, within NP, within P space, inside all of those. And these are proper containments. So you can actually prove that you can do more if you have quadratic time than if you have linear time. That if you have cubic space than if you have quadratic space, you can recognize more languages, provably. They're not the same. Okay. So the P is equal to NP question for those have been all solved by some major generalized theorems. So there's a lot of infinite complexity class hierarchies within these ovals of this Venn diagram. I just want you to have an appreciation of how complicated the picture really is. So far, we've seen a simplified version of it, even though it was an eyeful on this slide already. There's a lot more going on. And there's even more stuff that I'm not even showing you here, like the polynomial hierarchy that sits between P and P space. And there's even more stuff than that. The probabilistic Turing machines. Turing machines can flip coins. Turns out they can do more than regular Turing machines for a given complexity class. So there's a lot of unanswered questions about all of these, not just P is equal to NP, but hundreds and hundreds of other conjectures that haven't been resolved. In fact, P is equal to NP is a simple corollary to some of these other conjectures. That's how complicated they are. Much more so than P is equal to NP, some of them. All right, so there's a website called the Complexity Zoo. How many of you have looked at that on the web, the Complexity Zoo? It's on the website. It's a link. So there's almost 500 classes named that they're so important, so ubiquitous. People write PhDs on them every year and write papers, and there's entire conferences on them. And we gave them names like P and NP, polynomial space, polynomial time, non-deterministic polynomial space. But there's a whole catalog of them, and here are just some of them. So here's the probabilistic Turing machines, context-free languages, that's a class here, we talked about those, context-sensitive languages, co-NP, right? I'm just showing you an alphabetical list of some of these classes. Deterministic context-free languages like 0 to the n, 1 to the n, it's in this class here. And by the way, these are all live links on the web. If you click on them, you see the definition of the class, some examples of languages are in there. Here's exponential time, interactive proofs, logarithmic space. Here's what we just defined a few minutes ago, deterministic space f of n and deterministic time f of n for any f. So these are not just classes, they're families of classes parameterized by the functions f, all of them, all functions, all computable functions f. And there's more. Here's NP, non-deterministic polynomial time, non-deterministic logarithmic space, non-deterministic exponential time, and on and on and on. Non-deterministic polynomial space, which we already said the same as deterministic. Polynomial space is a corollary of Savage's theorem. Here's our favorite P, polynomial time. Most problems that we solve in everyday life, most problems that you'll be solving by programming for whoever you work for one day will be in this class, polynomial time. There's very few algorithms that are useful that don't run in polynomial time. By definition, if they run in exponential time, it'll never terminate in reasonable time by reasonable being within the lifetime of the universe, never mind our own lifetimes. Here's polynomial space and a bunch of others. Regular languages, we talked a lot about those right here. Here's the enumerable, the recursive enumerable, or what we call in this class the recognizable languages. These are right here in this class. Each one of these classes is a huge infinite set. It's very complicated, and so the halting problem is located right in this red oval, the recursive, or I should say recognizable languages. I keep saying recursive because that's a name that they used to have back in the 70s and 80s and even 90s. Later, we just started calling them recognizable languages. It's just a name switch. All right, so here are the containment of some of these categories, some of these classes. Now, this is similar to the Venn diagram I showed you all along, like 10 minutes ago. Except here, there's too many to show in a Venn diagram. It'll be a complete mess. So instead, I'm showing it as a graph, and this was constructed by Scott Aronson. You read some papers by him already, who can name the larger number. He's a quantum computation guy from MIT. And an arrow going up from one node to another node means it's containment, it's set containment. So at the bottom, you have the empty set, and at the top, you have the set of all languages, 2 to the sigma n. And in between, you have a whole bunch of other sets, classes of languages. Each one of those sets is an infinite class. of languages, each one of which is infinite in itself, or sometimes not infinite. But so there's a lot going on here, and I'll show you a little bit more detail, just so at least once in your life you see the bigger picture, get an appreciation of all the complexity classes of which we just talked about a few in this course. Okay, so starting at the top, here's all languages. That's 2 to the sigma star right there at the top, right? So first we'll slide all the way down just to get more details. Again, nodes mean complexity class, like P or NP. Arrows mean containment, set containment, a Venn diagram notion of set containment. So now you're seeing a little more detail of this. By the way, all this is on the website, on the Complexity Zoo. It's live. You can click on any one of these and see all the supersets, the subsets, links between them. Everything will be colorized and get live, and it's real funky to explore this. You can probably spend days just exploring this based on the names, never mind exactly what these actual sets are. Each one is, you can study each set for hours or days or even years. Some people make a living out of studying one of those ovals and its relation to one or two other ovals. And that's their entire career. It's that deep, that complex, that important. All right, so back to the top of this diagram. There's 2 to the sigma star. That's all languages, all of them, all possible languages, the power set of sigma star. Here are the recognizable languages, which of course is a subset of, everything is a subset of 2 to the sigma star. Here are the decidable languages, which is a special case of recognizable. Remember, decidable, you can always tell the yeses and the nos both in some finite time, never mind how fast or slow. But the halting problem is not one of these, but it's one of those. So the halting problem sits here, but not here. But this is still a subset. All right, here's exponential space. Here's non-deterministic exponential time, which is a subset of exponential space. Here's deterministic exponential time. And finally, polynomial space is over here, P space. All functions, all problems can be recognized or computed in polynomial space. So I'm just highlighting in red a few ones which we know and love that we mentioned. Some of them we even studied quite a bit, recognizable, decidable, and so on. Here's the next bunch down from the polynomial space. So now we went down in this diagram. Again, these are all set containments as arrows, Venn diagram set containments. So now I'm showing you a much more detailed map of the slide I showed you a few minutes ago that I drew with all these ovals. This is from the website, and it has hundreds of these classes, not just a few dozen. So here is polynomial time right here, P. So P is a subset of NP. Where is NP? Right here. So polynomial time is here. Non-deterministic polynomial time is there. But look, there's a bunch of stuff in between them, sandwiched between them. To get from polynomial time to non-deterministic polynomial time, you can go through this class and this class and this class and finally to NP. So you have set containment chains here, some of which we know are proper, some of which we know are not proper. They're not proper containment. There's stuff in the higher ones that is not in the lower ones. Their difference is not empty. And many others which we don't know either way. They're open questions. Okay, so for example, we know that between P and NP, you don't have equality here, 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 and here. Otherwise, you'd have equality between the two ends, P is equal to NP, which is still open. So that implies many, many other theorems just by looking at this. Here's non-deterministic linear space. Well, whatever. I don't want to harp too much on classes that we haven't talked too much about. And here's the bottom third of the diagram. So here's polynomial time, deterministic polynomial time. That's P right here. Almost every problem we solve in real life is in this little red oval over here. But look, there's lots and lots of everything in between the regular languages and P. Here's deterministic context-free in general, allowing non-determinism. We know this containment is proper. Like palindromes, you can solve non-deterministically with a PDA, but not deterministically. So this containment, for example, right here is proper. And of course, we have context sensitive. We haven't mentioned too much about that, but we keep saying context-free, 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 which suggests that some things are not context-free. They are context sensitive. And if we have time, we'll get back to that notion of context sensitivity. But anyway, here are the regular languages. Look at that. They're pretty much near the bottom. Here's the empty set right here. That contains nothing. That's a proper subset of anything else that contains something. So that's sort of the root of everything. Of course, at the top, we have to do a sigma star. It's all possible languages. And the regular languages, you see, as complicated as they are, because they have all languages which are denoted by regular expressions, for example, which includes the syntax of arithmetic expressions and lots of things, it's still pretty close to the bottom in terms of complexity. And of course, all of those can be determined in deterministic linear time, which is up here. So deterministic linear time not can only determine or solve or recognize the regular languages, but lots of other things in between. Okay. Any questions about any of this? So for the first time, I'm showing you the much bigger picture. It's like instead of the solar system, I'm showing you the whole galaxy now. Yeah. Majority? Oh, the problem of determining, you have n elements, and you want to know the majority element. That's it. It's as simple as that. If I give you n numbers, I say, does any number occur half or more times? That's it. As simple as it sounds, it's an interesting problem. All right, any other questions about that? About the bigger picture? So you can spend literally a career studying a few of those ovals. And people do that. And we get all sorts of interesting results. And these results lead to amazing breakthroughs in cryptography. How many have used cryptography today? Any form of cryptography today? Good. It's good that you know that. Where have you used it? Yeah, every time you surf the web, whenever you see a HTTP, S or some S in the HTTP prefix, you're using public key crypto. Every time you go to your bank website or to Amazon, or you're using cryptography, whether you realize it or not. And some of these cryptographic results come directly from the study of these containments relationships among these complexity classes. So it's not just pie in the sky, some theoretical concept. You're using every day, whenever you get on the web, or go to your bank, or buy something from the internet, you're using results that came from these studies right here, among many other things. Okay, so I want you to know it's very, very practical. It's not. So here's my little measly diagram. Now you see how simpler my diagram was than all of this. Of course, I wanted to ease you into it. If I show you this whole thing on the first day, you may get scared. But all this diagram here, with this going up for 3 whole slides, it's just a generalization of what I've been presenting all along, of this simplified version. Any other questions or comments? There's a lot going on in all of this. That's an understatement. All right, so again, my diagram only focuses on a few things, and in this course we only have time to focus on a few things. And as we go forward, we'll focus on 2 more things, specifically on P and NP. And we'll try to show the relationships between polynomial time, deterministic polynomial time, and non-deterministic polynomial time, and there's a lot of insights right there between these two. And these are just 2 ovals in this much bigger picture. And of course, already mentions lots of infinite hierarchies going on. So now we're focusing back down on the smaller diagram from this big picture. And in particular, we're going to focus on these 2 red classes right there, P and NP. And we're about to jump into NP-completeness, the study of NP-completeness, which by itself is pretty deep and interesting and amazing and very, very practical. All right, so with that introduction, let's talk about NP-completeness. So it's pioneered by Stephen Cook and Leonard Levine and Richard Karp back in the early 70s. It's a study of tractability, what's possible and not possible to do efficiently. By efficiently, we mean polynomial time. And we measure how long things take. It's not just whether it's decidable or not. It's how decidable is it within how long of a time, whether it's linear, quadratic, cubic, or exponential altogether. And it turns out that it seems that verification of an answer seems to be easier than computing it yourself. In other words, if somebody whispers an answer in your ear, you can pretty much scratch your head a little bit and tell if they're right or not once you hear an answer. And that seems to be easier than actually coming up with the answer by yourself without, in a vacuum, without hearing a possible answer that you can verify. And NP-completeness helps all of us determine the relationship between verifying answers and just computing them. So for example, if I say, here's a list, sort it, it takes n log n time to sort, even the fastest sorting algorithm like merge sort. But if I say here's a sorted list, verify that it's sorted, that takes only linear time. You just go from end to end, make sure everything is higher as you go into it than whatever you saw before, and then that's verification in linear time that it's sorted. So verifying that something is sorted takes less time than actually sorting it. And without NP-completeness, we weren't sure why, and that helps shed light on questions like that. Also, it helps you examine the power of non-determinism. So deterministically, computation is just a long list of state changes, but non-deterministically, you can start bifurcating and have many next states, and the computation begins to look like a tree. And NP-completeness helps us determine the relationship between determinism and non-determinism, whether non-determinism is a special power, it's a superpower, or not. For some complexity classes it is, others it isn't. And for polynomial time, we still don't know. That's the P is equal to NP question. So these are advantages or uses of NP-completeness. Before we dive into it, I want to motivate why we're doing this. It helps you deal with notions of encoding, of transformations, reducibilities of problems to other problems. We already saw some examples of reducibilities when we talked about Rice's theorem and examples leading up to Rice's theorem. And of course, there's a million-dollar question, P is equal to NP, and many sub-questions and super-questions around that. Some super-questions around that will imply this is a simple corollary, which means they're a much harder question than this. And of course, some questions are easier than that we already solved, and some are still open. And the notion of completeness is the notion of which problem is the hardest for a given class, whether it's P, NP, P space, or what have you. And that's good to know, because if you're trying to solve a problem that's hardest for the class, which means if you can solve it, you can solve everything in the class in less time or space than it. If you're looking at a complete problem that you're trying to solve, you pretty much you can be sure you have a very tough nut ahead of you to tackle. So you may want to think twice if you're trying to solve such a problem efficiently. So the study of these algorithms and problems and functions is not just about what you should do, i.e. try to solve something in polynomial time, assuming you know it's in P, but it's something that you perhaps shouldn't do, is try to solve a problem that you know is in P space and is P space complete. You probably shouldn't try to solve that efficiently. Why? Because if you could, P space will be equal to P, and NP is sandwiched in between, and P is equal to NP will be true automatically as a simple corollary of your solution, efficient solution to a problem that's P space complete. So, which means it's a very, very hard problem, which means you should be waved off trying to solve it precisely, exactly, brute forcishly, and instead come up with heuristics if you still need to solve it, like traveling salesman or bin packing or satisfiability. We'll talk about those problems. So NP-completeness tells you not only what you ought to do algorithmically, but what you ought not to do algorithmically, because you'd be wasting your time. And up until the 70s, when this theory was developed, companies, individuals, groups, universities tried to solve all sorts of intractable problems. They spend billions of hours and billions of dollars trying to solve problems exactly that now we know are not likely to be solvable exactly, like traveling salesmen and scheduling and routing problems and Steiner tree problems. And now we know they're NP-complete. We know we shouldn't bother trying to solve them exactly because it's probably a waste of time. Instead, we come up with heuristics. But before that, it wasn't so clear. And so this theory not only saves time on the positive end, what you ought to try to do, but it saves time on the negative end, what you shouldn't try to do, because it's probably hopeless and futile. Okay, so it's quite an amazing theory. It slices, it dices, it does a lot of things for us. So, you know, it's hard to overestimate how useful that is. Okay, so here I'm just kind of recapitulating all these motivations I just mentioned. It could save you literally billions of dollars to companies, tell them what they shouldn't try to do efficiently, and it helps you transform problems to other problems. If you solve something already, you know if you can transform it to another problem, that that's also a solution to that problem, this other problem, by some transformation, and you've already solved multiple problems by solving that one. So that's a very, very useful thing to do because it gives you leverage. You solve one problem, and you've solved many, right? So if you solve one complete problem for the set, like satisfiability or graph coloring or traveling salesman or Steiner trees, you know that you can, using that algorithm, if it's efficient, you can solve the entire class with the same efficiency. So when we talk about NP-complete problems, it's one problem to rule them all. right? And that's a very, very powerful tool. They're all bunched together. Together they stand, or together they fall, algorithmically speaking, with respect to efficiency. All right, so it gives you license to approximate without looking foolish by somebody preempting you with an exact solution the next day that runs even faster than your approximation. So once you know something's NP-complete, it gives you license to approximate it without having to worry that you're barking up the wrong tree, because you may be able to do it exactly, also efficiently, without approximation. So if you want to implement, say, multiplication, we know how to do that efficiently. You don't want to say, I'm going to have a heuristic for approximation, for multiplication that approximates the right answer, the right product. I mean, you could do that, but it's kind of silly because we can also compute the exact, correct, right product without approximating, and it'll just be as efficient as approximating it. So certain things you don't want to approximate, not because you can't, but because you can solve them exactly just as easily. So you might as well go for the exact answer, not some approximate answer. Right? NP-completeness allows you to determine which is which and when is when. Okay? And of course, it helps you understand the notion of parallelism, because non-determinism is a special kind of generalized parallelism after all. And all these classes have completeness theories to them. It's not just NP-completeness. You can talk about p-space completeness, exponential time completeness, linear time completeness, logarithmic space completeness, and so on and so on. Of course, in what comes next, we'll mostly talk about NP-completeness, completeness of polynomial time and non-determinism thereof. Okay, and it helps you illuminate the relationship between problems or between algorithms. It gave rise to a lot of interesting mathematical concepts and theorems that are very general. And it decouples the actual implementation platform from the results and the theorems and the observations and the insights, because remember, P and NP are implementation independent. They're exactly the same class of languages whether you're talking about an iPhone, a supercomputer, a cloud computer with millions of processors, or just an abacus, a very primitive device. All these speeds don't vary substantially, only by a constant. And of course, in some cases, the constant is large, but asymptotically, it's exactly the same class. So if you can prove something for that class, you can prove that thing for all of these computation models, including DNA computers, billiards, Tinker Toys, Legos. So it's very, very robust results. You don't have to prove the same result for abaci, I guess, plural, and then separately prove the same result for iPhone, and then separately prove the same result for laptops, and then for supercomputers, all separately as if they were all different. This ties them all together asymptotically. So it gives you that leverage. You get a lot of bang for your buck from this theory. All right, so don't forget that it's also fun and interesting and cool, intellectually stimulating. It's always a good thing to study something because it's fun. Never underestimate that. All right, so let's get technical. So this is the old definition from a couple of lectures ago. A language A is reducible to a language B if there exists a computable function that takes A to B. How many remember that with this picture? Okay, now we're going to get funky and nuanced about this. And the nuance is F is not just a computable function. It's not enough for it to exist and be computable as opposed to be undecidable. It's going to be computable within polynomial time, necessarily. And we said once you have this picture and the old definition, A reduces to B, and that's notation, A reduces to B, which means, if you can solve B efficiently, you can solve A efficiently, or if you can solve B at all, you can solve A also, because reduce A to B, solve it in B, and then you know the answer for A, because this function preserves membership, right? So these are two languages, A and B. They have strings in them. Some strings are in, some are out of the language, but it preserves membership so that if you have a string here that's in A, you hit it with F, and you end up with a string that's a member of B necessarily. And if you have a string not in A, and you hit it with F, it won't end up in B. So it preserves membership, it preserves non-membership. Okay. Now here comes the nuance. It's the red stuff. It's polynomial time. So now we take out a stopwatch and we say, okay, it's not enough to say that something can be done any old which way. I want it to be done efficiently, and I'm watching the clock now. By efficiently, I mean polynomial time, not exponential time or anything bigger than that. There's plenty of functions that are bigger than polynomials, right? So now we redefine this transformation, except throwing a clock on it, timing it, and saying a language A is polynomial time reducible to a language B if there exists a computable function f, and now f has to be computable or runnable in polynomial time, not just any old time. Okay, so exponential time is no longer allowed. It's not sufficient for f to be decidable. It has to be efficiently decidable. So f has to be a member of P, the class of languages or functions that are computable in polynomial time. And we're watching the clock. We're making sure that the time is polynomial, and f must run in that time. If it doesn't, it's not one of those. All right, so we basically put a time bound everywhere in this transformation, in particular on f. Really, that's the critical point where we're timing things. So now we say f is polynomial time reducible, polynomial time reduction of a to b. That means a reduces in polynomial time to b, which means f runs in polynomial time and preserves members to members and non-members to non-members. So if you can solve something efficiently in B, by efficiently I always mean polynomial time, any polynomial, square, cubic, quartic, but not exponential. That's not a polynomial. So if something is solved polynomially efficiently in B, and f runs in polynomial time, now you can solve stuff in A in polynomial time also. How? Transform it into B, solve it in B, and you know the answer to A. Because f preserves members to members and non-members to non-members. F preserves membership. So just like before, when we talk about decidability, right? If f was decidable and B was decidable, A is decidable too. How? Transform it to B, solve it in B, and you know the answer to A. So you're deciding in A via the proxy B, the algorithm for B, and of course the transformation that takes you there. Now, the same thing is true not about decidability, just decidability, but also efficient decidability. How many sort of get this? All right, any questions so far? Because we go a lot deeper into this. Any questions so far? What we're doing? We're doing what we did before with transformations, with reducibilities, but now with the extra complication that we're watching the clock. Things not just have to be doable, they have to be doable fast. By fast, we mean polynomial time. Question? Yeah, it's like a homomorphism in mathematics or commutative diagram kind of thing, but not exactly, but it's similar. It's the same notion. You're mapping things to other things. So f is a function, and here it must operate in polynomial time. It can't operate in exponential time or anything that's not polynomial. So in this scenario, f must run in polynomial time. Say quadratic time or cubic time. So f is relatively easy to compute. It's not going to take exponential time to compute. It's part of the definition. Now, there's plenty of f's that take a long time to compute, much longer than a polynomial. They just don't belong in this slide. So I'm focusing on efficiently computable f's, transformations, fast transformations. By fast, again, I mean polynomial time. Now, n to the fifth might not sound that fast from a practical point of view, but it's a heck of a lot better than 2 to the n. That's much, much slower than n to the fifth, asymptotically speaking. So again, fast, efficient means polynomial. What degree? Any degree you want. But even the smallest exponential is bigger asymptotically, grows faster asymptotically than the largest polynomial. So you can take n to the 100 as very, very slow polynomial. N to the 100 is kind of a lousy polynomial in terms of efficiency, but it's still a lot better than 2 to the n. From some point on, 2 to the n will be larger than n to the 100. How many understand that? Good. Any other questions? Now, of course, within polynomial time, we want to be a lower order polynomial than a higher order polynomial. So n squared is much better than n cubed. And both of those are much better than n to the 100, don't get me wrong. Of course, linear time is better than any of those. And that's okay, but collectively, they're all better than some exponential. Okay. All right, so that's what we have so far. We modified the transformation to run efficiently. And basically, this slide here, this simple-looking, innocent-looking, deceptively innocent-looking slide is the basis of all of NP-completeness. Just like the one without this red time bound was the basis of all of Rice's theorem and much of undecidability theory. As innocent as it looks, as simple as it looks, there's a lot going on here. It's a heavy power tool, mathematically, philosophically speaking. Okay? And now we're going to start applying this. So we say A reduces to B with a little p here, which means it's in polynomial time. Before, we didn't have this p here. Now, we do. And intuitively, we're saying that A is not harder than B modulo some polynomial, the polynomial p that is polynomial time. Any polynomial. And we can immediately start proving theorems. We can say that if A polynomially reduces to B, and B is decidable in polynomial time, then so is A, decidable in polynomial time. Why? Let's say you don't know how to solve A in polynomial time, but you know how to solve B in polynomial time. And you know how to transform strings from A to strings of B in polynomial time, and non-strings of A to non-strings of B in polynomial time. Now you can decide B in polynomial time as well. How? You don't know how to do it in A directly, so transform it to B, solve it in B, and you'll know the answer to A. Now, how long does it take to transform? Polynomial time. It says so right here in the F. Right? How long does it take to solve in B? We already said polynomial time. That's part of the theorem. If B is decidable in polynomial time. That makes A decidable in polynomial time too. Again, take the A, you don't know how to solve it, fine. Take it over to B. Solve it in the B domain fast, and that'll give you the answer to A. The answer is if and only if. It's a member in B if and only if it's a member in A, because remember, F preserves membership. Right? A string in A takes you to a string in B through F. And non-strings in A will take you to non-strings in B. So membership is preserved. So you can determine membership in B, you automatically determine membership in A. And F gives you this correspondence. It doesn't have to be onto, doesn't have to be one-to-one function, but it must preserve membership. All right, so if you can solve B efficiently, and you can transform things from A to B efficiently, you can solve A efficiently. How many get this? All right, good. That's a lot of people. Excellent. I'm proud of you, my Padawans. All right, but let's continue, go deeper. This is the contrapositive, like the previous theorem without all the red stuff. If A reduces to B and A is not solvable in polynomial time, then B can't be solvable in polynomial time either, because if it was, A would be solvable in polynomial time, but A isn't. That's the premise of this second theorem. So the second theorem is a contrapositive of the first, or you can prove it from first principles by reasoning it all out like we did the first theorem here. Either way, you have this theorem. So already it gives you a tool to reason about problems when you don't know much about them, except that you have some transformation from some other problem into them. It gives you a tool to solve problems using other problems, using the algorithms for other problems. Okay. So for example, let's say you try to find the minimum element of a set and you don't know how to do it. Let's say you don't. I mean, it's pretty straightforward to do, find the smallest element in a set. But let's say you don't know how to do it, but you know how to sort. So how would you find the minimum if you have a subroutine for sorting? Yeah, sort, and then the minimum is the first. So if you reduce the problem of finding the minimum to the problem of sorting. And because we can sort quickly, we know you can find the minimum quickly. Sort, and then it's the first. That's a transformation. How many see that? It's not a very complicated transformation, but it's one of those transformations nevertheless. Right? So you see, solve problems using other problems or solutions to other problems as a quick way of solving these other problems that you may not know how to solve. Now, for sorting in a minimum element, it was pretty obvious you can also find the minimum without sorting. In fact, it's faster. But let's say you didn't know how to find the minimum, because some of these problems that we're going to talk about, it's not clear at all how to solve. But if we can transform to some other problem and then solve the other problem using some way, we're also solving the first by one fell swoop, which is great because it gives you leverage. You only have to find solutions to a few things, or one thing even, and you're already solving lots and lots of other things that transform to it efficiently. That's the idea here behind NP-completeness and these transformations. So to solve a problem efficiently, transform it to another problem, and then use the solver for this other problem to solve that new problem efficiently, and then you're solving the old problem efficiently too. Remember that diagram. It'll come back to haunt you many times. Maybe I should say come back to help you many times. Haunt sounds like a negative thing. Help is good. All right, so satisfiability is the problem of I give you a Boolean formula, like this one in purple, and I ask you, is there a way to assign the variables that will make this formula true? Yes or no? It's a Boolean function. Right? So x and y and x prime and one, x prime means not x and y prime means not y. These are all Boolean variables, x and y and z or whatever. And the question again is there a way to make the whole formula true? I don't want the formula to be true all the time for any assignment necessarily, but is there a way to make it at least one assignment that will make the whole formula true? That's it. That's the problem of satisfiability. So some functions are satisfiable, others are not. And it turns out it's very hard to tell which is which in general. Now for simple functions like this, it's pretty straightforward because there's not a whole lot going on except a couple of variables. But if I give you a Boolean formula of 100 variables or 1,000 variables or 1,000,000 variables with lots and lots of complicated and or kind of conditionals with some of the variables negated, it may be very, 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 very difficult to tell if it's satisfiable or not efficiently. Now, if you don't care about efficiency, you can tell very easily if efficiency wasn't an issue. Somebody described to me how to solve the problem of whether such a formula is satisfiable if efficiency didn't matter. You can be as inefficient as you'd like. How would you do it? Try all combinations. How many see that? Brute force it. How many combinations are we talking about if we have n variables, n Boolean variables, x and y and z and w, n of them? How long does it take to try all combinations of the variables to see if one works, to make the formula satisfiable? 2 to the n. There's n Boolean variables. Each one can take 2 values, true or false. Yeah, so after 2 to the n time, you'll know. But 2 to the n is very, very slow. Okay? Way too slow for any practical purposes. Right? I mean, 2 to the 30 is already a billion. 2 to the 40 is already a trillion. Computers just aren't that fast. Okay, so what we can do, though, is in order to solve this, you can transform it to a graph problem, graph colorability in particular. And graph colorability simply says, I give you a graph, undirected graph, just graph, nodes and edges, and I ask you the question of, is there a way to color the nodes of this graph, say using 3 colors, such that no 2 adjacent nodes share the same color? So no neighbors can have the same color. Neighbors must be different colors. So I say, is there a way to 3-color this graph? How many say, yeah, there is a way to 3-color this graph such that no 2 neighbors share a color? Okay, it's pretty straightforward for this graph. Turns out, if I give you an arbitrary or a large graph, it's very, very hard to solve that. In fact, it's NP-complete. We're going to prove that. But let's say you had a way of solving graph colorability, some subroutine, some black box, some way of solving graph colorability. By the way, here's a 3-coloring of this graph. No 2 adjacent nodes share a color. It turns out that you can take satisfiability, transform it to graph colorability problem in such a way that it's an if and only if. This formula is satisfiable if and only if this graph is 3-colorable. I'm not showing you exactly this transformation right now. I'm just telling you it's possible to do this. We will do this. We will prove this. Not today. It's tricky. Probably take 20 or 30 minutes just to prove that. So, but you can show that you can take a problem of satisfiability and transform it into a problem of colorability in such a way it'll be if and only if. This formula will be satisfiable if and only if this graph will be 3-colorable. So what we're doing is one of these. How many get it? Good. So that means if you have a solution algorithm for colorability, you can exploit it into solving satisfiability for you. which means we are just reducing satisfiability to 3-colorability. In this diagram, satisfiability is the A and colorability is the B. The set of all satisfiable assignments or formulas is the A, and the set of all 3-colorable graphs is the B. And F is this transformation which I'm telling you exists, but it's a complicated function. I'm not telling you right now exactly what this transformation is. I'm just telling you it can be done, we will do it, we will prove it a little bit later. Okay, so NP-completeness is all about transformations, transforming things to other things, and then, being amazed at the consequences of doing that. Very, very powerful technique. Any questions so far, where we're going? This is like a high-level goal. All right. By the way, where did this come from? Anybody recognize this allusion? Anybody read the novel by Franz Kafka that this cartoon is referring to? Metamorphosis. Yeah, somebody has a classical education here. That's good. Hopefully you all do. I mean, we're a pretty good school. All right. So a few definitions. Again, these definitions, they seem innocent and simple, but they're subtle and far-reaching, a lot like the rest of the definitions in this course. So don't let it fool you. There's a lot going on, even though it's succinct, it's innocent sounding. It's actually very deep and profound and far-reaching in its implications. All right, first definition. So a problem is NP hard if two things are true. Every language in NP reduces to it in polynomial time. And it could be a different reduction, a different polynomial for every language in NP. Let's step back. What is NP? NP is all the languages or functions, equivalently, that can be computed in non-deterministic polynomial time. Which polynomial? Any polynomial. So NP is this large, infinite set of languages. Each language itself could be infinite. So it's a complicated object. Make sure you understand the type. Don't let the types run away from you in your mind. Keep your tight lock with your mind on the types of the object, never mind the exact values of the objects. So if every problem in NP reduces to this problem in question, L prime, in polynomial time, by definition, that problem is NP hard. It means it's as hard as anything in NP. Because if you can solve it efficiently, all of NP can be solved efficiently. Why? Because transform in polynomial time some problem in NP to it, solve it supposedly efficiently, and you're solving any problem in NP efficiently too. Just like we used sorting to solve the minimum problem a minute ago. So that makes that problem as hard as anything in NP. How many get that? Okay. About half of you, all right. I'll take it. It's the first time we're seeing this definition. It's good. All right. Second definition. A problem is NP complete if it's NP hard and that problem in itself is in NP. Because remember, that problem L prime didn't have to be, this is supposed to be L prime, by the way. This is a typo. I caught it before you, so no extra credit, but it's a typo. So L prime didn't have to be in NP. Now we're saying it is. And if it is in NP itself, it's not just NP hard, it's NP complete. So NP complete is a special case of NP hard. And the distinction is, still everything reduces to it in polynomial time. Everything in NP reduces to it in polynomial time. But it itself is also itself in NP when it didn't have to be. Okay? So two slight variations on the same theme. They have in common that everything in NP reduces to them. That makes it NP hard right away, that by itself. But if in addition, that problem L prime in itself is an NP, it's not just NP hard, it's NP complete. So NP complete is a subset of the NP hard problems. How many get that? It's this extra condition. Now, look, these definitions are simple. They're each one less than a line. Actually, one is half a line. But amazing results and incredible theorems and very complicated consequences and insights will flow from these two simple-looking definitions. All of NP-completeness does, in fact, and many other things. Okay. So if one NP-complete problem is in polynomial time, deterministic polynomial time, that immediately implies that P is equal to NP. Why? If a problem is NP-complete, NPC means NP-complete, right? It's this definition here. means everything in NP reduces to it in polynomial time. So to solve anything in NP, reduce it to this problem that could be solved in polynomial time, solve that problem from polynomial time, which means you're solving this other problem in polynomial time. That problem is an arbitrary problem in NP. So if a problem in NP complete, the set of NP complete problems is, if one of those ends up in actual deterministic polynomial time, they all are. By they, I mean all of NP. All right, so here's the picture. This is a small, tiny piece of this larger diagram that we kept showing over and over throughout the course. Here's NP and here's P. And P is a special case of NP. Why? Non-determinism is a generalization of determinism, or conversely, determinism is a special case of non-determinism. So you got this Venn diagram containment, and we don't know if they're equal. That's worth $1 million. That's still open. But here are the NP-complete problems, like satisfiability, whether a Boolean formula is satisfiable or not. And if one of those problems is in P, all of NP is in P, because all of NP reduces to it. That's why they're NP-complete, just like it says so in the definitions. NP-complete if it's NP-hard, which means everything in NP reduces to it. And if you can solve it in polynomial time deterministically, all of NP can be solved in polynomial time deterministically by going through the reduction, solving it deterministically in P, and then knowing the answer for the NP problem. How many understand all of that? All right, it's less hands, but we're starting to wade into deeper waters here. And we'll keep going. So you want to ask me some questions so far, or any confusions, or what are we talking about? Or maybe I'll just repeat it and see if you have any questions in 60 seconds. All right, so we made a definition. We said a problem is NP-hard if anything in NP reduces to it. What do I mean reduces? I mean this. Okay. So when we say we see a reduction, transformation, always keep this picture in mind. I know it's a simple looking picture, but already you saw how deep it gets when you start applying it and picking up specific transformations, and transforming certain specific problems to other problems. This picture is abstract. Right? It shows you some problems, some other problems, some way of transforming instances of one to instances of the other, but you can apply it many, many different ways. So, but generally you have transformations, and soon, probably in a lecture or two, we'll see specific complicated transformations like satisfiability into colorability. All right, so here comes the definitions again. The problem is NP-hard if everything in NP reduces to it in polynomial time. Okay? And it's NP-complete if what I just said plus the problem itself is in NP, which it didn't have to be for just hardness as opposed to completeness. All right, so here are all the problems, NP-complete problems like satisfiability. We haven't proven yet that satisfiability is one of those NP-complete problems. We will when we talk about Cook's theorem soon enough, probably beginning not in the next few minutes. But here are all the problems where, for each one of these problems it's NP-complete, all of NP can be reduced into one of those in polynomial time. And if one of these problems can itself be solved in deterministic polynomial time, in other words, if one of these problems here was inside P, all of NP will be inside P. Why? Because you can solve each one of the NP problems in polynomial time by transforming it into this problem that was itself in P, and then you'd have an efficient solution to an arbitrary problem in NP, just like we can solve the minimum problem using sorting from the example earlier. Okay, so here's the co-NP complete problems, which is the complements of all the problems in NP. Right? It's not all the stuff that's not in NP. It's for each thing in NP, complement it, and you get a new problem, and that problem is in co-NP. So of course, the complement of P is P itself. So if we take the complement of one of the languages that can be solved in polynomial time, you can solve the complement language in polynomial time too. And why is that? See if you get that. If I can solve something in polynomial time, determine membership in a language, or solve membership in a language in polynomial time, why can I also solve membership in the complement of the language in polynomial time also? Yeah, take the answer and just say the opposite. Be contrary. Just negate the answer to the first, and you get the answer to the complement. It's pretty straightforward. So P and co-P are the same class. How many get that? Good. That's a lot of hands. I like that. But for NP-complete and co-NP-complete, or NP and co-NP, we don't know if they're the same. These are open questions. So if NP is the same as co-NP, that's an open question. We don't know. Just like P is equal to NP, we don't know that either. But if something is in P, its complement is in P, so P complete let's not define P complete. I mean, it's easy to do. P complete is, if everything in P reduces to it but you can't say polynomial time anymore because it's already in polynomial time. So you got to say logarithmic space. But having said that, let's say don't worry about it for now. But I said it anyway, in case you were curious. All right, so we don't know if P is equal to NP, but we don't even know if NP is equal to co-NP. That's open also. But if NP is not equal to co-NP, then P is not equal to NP as a corollary because P and co-P are the same class. P is equal to co-P because you can negate all the answers. Solve the problem in P, negate it, and you're solving the complement problem. So P and co-P are the same class. But we don't know the same for P and NP. And we don't know the same for NP and co-NP. So there's several open problems here, as well as a few problems that are trivially not open. All right, back to satisfiability. So satisfiability says you have a Boolean formula, and it's given to you as a product of sums. So for example, here's a Boolean formula, and of course, as you already know, plus means disjunction is or. Times right there means conjunction, it's and. So I'm just representing or and as pluses and times respectively, just notationally. And little apostrophes means the complement of the variable. Or you can put a bar over it, that's a complement too. I like apostrophes because it's easy to do without worrying about the bars. So here's a bunch of variables. They're all Boolean variables. Each variable is 0 or 1. The question is the formula satisfiable? Is there a way to assign the variables any which way you want, as long as the overall computation of the formula with the ors and the ands all computed out, it ends up being true? Okay, that's just conjunctive normal form means product of sums. So that's a canonical way to represent the formula. You can represent it lots of other ways, but let's just stick with that. So a formula is satisfiable if it can be made true by some assignment of the variables. Which one? I don't care. You tell me. But some formulas, it's possible to satisfy them with some assignment. Others, no matter what you plug in, it won't work. Right? So the problem with satisfiability is I give you the formula, and you tell me whether it's satisfiable or not, and you better be right. Now, notice, I'm not asking you to give me the satisfying assignment to this. I'm just asking you to tell me whether it's satisfiable or not. It's a major difference. If I ask you to give me the assignment, that's at least as hard as telling me whether it's satisfiable or not. Because if you give me an assignment, I can plug it in and tell for myself if the assignment works. If you tell me it's satisfiable, that doesn't necessarily give me an assignment. It just tells me that it's possible to find an assignment that will make the formula work, but it doesn't tell me which one it is. Right? It's like when somebody says, believe you me, the following is true, but they're not telling you why it's true. And it's not very satisfying. Right? Okay. So for example, x plus y times x bar plus z bar is satisfiable. For example, you let x be 1, let z be 0, and you'll see that this term becomes 1, this term becomes 1, the product is 1, the whole thing is equal to 1. Fine, that works. That assignment works. Other assignments may not work, but it doesn't matter. This assignment works, it's satisfiable. That's it. On the other hand, this formula here is not satisfiable. Why? To make this satisfiable, this clause here, x has to be 1 or z is equal to 1. If both x and z are both 0, this whole thing will be 0 and the product will all be 0 and it won't work. So at least x must be 1 or z must be 1. But if x is 1, x bar is 0, and this 0 term here will make the whole thing 0. So that's no good. If z is 0, z bar will be 0. Excuse me, if z is 1, to make this true, z bar will be 0, which will negate through a product this whole other term. So there's no way to satisfy this assignment. How many see that? Oh, good. So some formulas are satisfiable, others are not. It turns out it's a very, very tough problem. Now, it turns out it's NP-complete, and we will prove this next time. But it's innocent looking enough so that you might wonder, why is it so hard? Well, because we know of no shortcuts on how to determine whether it's satisfiable or not for an arbitrary formula other than trying all brute force, all possible ways to assign the variables. we already mentioned that as exponential time. There's exponential number of possibilities. So it's no good. Okay. So the Cook-Levin theorem basically proves that satisfiability is NP-complete. Everything in NP reduces to in polynomial time. So in some sense, satisfiability is the toughest problem in all of NP, as innocent looking though it might seem. And that's a paper from 1971 that got this guy a Turing Award for this paper because it ushered in the entire theory of NP-completeness. It was just brilliant, one of the best papers ever written in terms of the result. All right, so the idea is basically you take a non-deterministic Turing machine computation that's arbitrary and show how you convert that to a Boolean formula in a way that this Boolean formula is satisfiable if and only if the Turing machine computation halts in polynomial time. Which means if you can solve arbitrary satisfiability for arbitrary formulas, you can determine automatically and just as efficiently what arbitrary Turing machines will do or not do in polynomial time, non-deterministic Turing machines. And that's sort of the crux of this proof, and next time we'll see a lot more details about that. It's full of kind of interesting details about Turing machines. And I promised last time to ask you about JFlap today. How many of you used JFlap so far? Oh, wow. That makes me very happy. And you see, when you start using it more, you'll get it more and more when I talk about Turing machines and how they work and what they do and what they don't do and how they change states. Now you know. It's better. So thank you for doing that. I really appreciate it. All right. See you next time.